Hi, my name is Joanna Holt and I'm the Education Manager of the Netherlands Research School for Astronomy, or NOVA. I'm also a Science Education Researcher in the Smart Education Lab of the Amsterdam University of Applied Sciences. Before moving into education and outreach roles 10 years ago, I worked for many years as an astrophysicist. Today I'm going to be talking about the project Stargazing Live, and this work has been done together with colleagues at NOVA, Radboud University and the Smart Education Lab at the Amsterdam University of Applied Sciences. Stargazing Live is a project which started in early 2021 with the aim of bringing semi-live real scientific data into the classroom. The data will come from the Meerlicht and Black Gem telescopes owned and operated by the Radboud University in Nijmegen, the Netherlands. Meerlicht is a small telescope based in South Africa which does optical follow-up for the radio telescope Meerkat. The Black Gem array is currently being built in Nicosia in Chile. The telescope design is the same as Meerlicht, but eventually there'll be an array of 15 telescopes. The scientific aim of Black Gem is to quickly respond to and observe the optical counterparts of gravitational wave detections. Each night the telescopes upload all of their data to Nijmegen, where it is processed automatically. My colleagues and I at NOVA are astronomy outreach and education professionals, and we also collaborate with the education researchers based at the Smart Education Lab of the Amsterdam University of Applied Sciences. But what are we doing? Our target group is upper secondary school physics students, 16 to 18-year-olds, studying at the highest level in the Netherlands, pre-university education. As such, they cover some fairly advanced topics in astrophysics. The main product is a new lesson for the NOVA network of mobile planetariums, which visit schools across the Netherlands. We will use recently taken real data to help explain topics related to the science goals of the telescopes, which are also taught in the school curriculum. This photo shows an image from the Meerlicht telescope of the Tarantula Nebula, displayed in the NOVA mobile planetarium. We are also producing a short full-dome film about the telescopes and their science goals, and planetarium modules are written in such a way that it is easy to modify the content for other age groups. In addition, we are creating support and lesson activities for 16 to 18-year-olds. The lessons use the interactive digital tool DynaLearn. The lessons challenge students to model key curriculum concepts linked to the telescopes and their science. The lessons were created using a co-creation model led by science education experts with significant input from astronomers, astronomy outreach and education professionals and physics teachers. And I talked about this co-creation model at the third IAU Shaw Workshop in 2021 in a talk entitled Co-Creation 3.0. The full project is now being extensively tested in secondary schools. The project is funded by a science communication grant from the Dutch Research Council NWO, and of course the resources will be made freely available in both Dutch and in English. Today I'd like to focus on the lesson activities created for the project. The lessons teach curriculum concepts using concept modelling in the interactive digital tool called DynaLearn. During the lessons, students need to think carefully about how the concepts work. Students work independently and are led through the lesson with a workbook. Teachers can monitor the progress of the students through the lesson via an instructor interface. The tool provides automated feedback, but teacher feedback can also be given via the chat function of the software, or of course live in the classroom. We've created two lessons, one on the balance of processes within a star and one on stellar evolution. Both topics are covered at the highest level of secondary school physics in the Netherlands. Before we take a look at the digital tool, I just want to spend a few moments focusing on the idea of concept modelling. There is a subtle difference between concept modelling and the more frequently used concept mapping. In concept mapping, students create something that looks like a mind map. It's purely descriptional. Students break up a concept into subconcepts and the relationships between them, and a concept map is static. Relationships between the subconcepts are descriptive. For example, the Earth has a shape. Concept modelling is a more active representation of concepts. As with concept mapping, students must split a concept into subconcepts and recreate the relationships between them. However, instead of creating a static verbal representation, the relationships which students place between subconcepts behave in the same way that the scientific formula behind them work. So think, for example, of causal dependencies between quantities. For example, as the wavelength of light from a star increases, the star becomes redder. Wien's law. The tool therefore not only allows the students to recreate the model, the static part, but also allows the students to simulate the model to check that the relationships are correct and to discover how various parameters change. Now I appreciate that this is all quite abstract, so I'd now like to re-explain this part with a short demonstration. This lesson leads the student through the construction of a concept model for star characteristics. The concept model includes objects or entities, such as a star, the core and the surface, properties, such as mass, gravity, density, etc., with associated measurable values, such as mass in terms of solar masses, etc. As you can see, the demonstration begins once some work has already been done in the DynaLearn interface. Before getting this far, the student has read an introduction to the lesson in the accompanying workbook and then logged into DynaLearn. And first they see a short video before arriving at a blank workspace. In DynaLearn, entities, properties and measurable values are denoted by different symbols. In this model, the student has started by placing the entity, the stars, and given the entity two properties, mass and gravity. The properties mass and gravity have been linked to the entity by two grey arrows, which represent basic relationships. The star has mass and the star has gravity. Both mass and gravity have associated measurable values, and these are denoted by the delta symbols with arrows. And at the moment, mass and gravity can either be reducing, the downward arrow, increasing, the upward arrow, or remaining the same, 0. Finally, mass and gravity have been linked by a positive causal dependency, blue arrow with a plus sign. This shows that when the mass increases, the gravity will also increase. We're now going to take a look at the next steps in building the diagram. First, the student attempts to add a second entity and calls the entity density. However, density is not an entity but a property, and so the software highlights this with red lines and a red question mark. This gives automated feedback. In this case, the name needs to be changed. The student then selects an appropriate name for the entity, core. The student then assigns the core a property and names this fusion energy. The student then links the properties gravity and fusion energy with a positive causal dependency. This again results in an error. Automated feedback informs the student that the student has created a causal dependency between two properties that is not correct. The student then removes the causal dependency and adds a second property to the core, density. The student then continues to add further causal dependencies. Once a section of the model is correctly completed, the student can model the relationships. The student does this by setting an initial value, here the blue arrow on the upward arrow of the mass. The student then clicks on the button to start the modelling. And as you can see, the arrow turns green and other green arrows also appear. This shows that when the mass of a star is larger, the gravity is also larger, which in turn would give a higher density and fusion energy rate in the core. This is now only part of the model that the student will create in the lesson. The student can monitor their own progress in the model with the bar at the bottom. This shows how many entities, properties, values, and causal dependencies and other relationships are still required to complete the model. The teacher can also monitor the progress of students through an instructor dashboard. In addition to automated feedback, the teacher can also give individual feedback via the chat function or, of course, in person. It is also possible for the researchers to remotely track progress. For the research phase of this project, student click data is also collected and analysed to improve the lessons. The project is now in the testing phase. During this period, we will test the planetarium and DynaLearn lessons in 11 classes in 3 schools across the Netherlands. We'll also run multiple workshops at the largest physics teacher conference in the Netherlands. Initial tryouts at several other teacher events have also taken place. We are evaluating the planetarium lessons using observations and interviews with students and teachers, and the lesson activities are being evaluated with a more formal evaluation, including pre- and post-testing, to measure the learning gains during the lesson activity. So to summarise, Stargazing Live is an innovative project which aims to inspire students and teach key curriculum topics. The project comprises new planetarium lessons, including a semi-live data link to the Meerlicht and Black Gem telescopes. Complementary lessons for the highest level of secondary physics education have been created using DynaLearn, an interactive tool for concept modelling. The project is also being extensively tested in schools. I hope you've enjoyed this presentation, and if you'd like to know more, please don't hesitate to contact us. Thank you.